Hello everybody, welcome back to ECE 310. This will be an online learning adventure. I am currently in Huntsville, Alabama. As you can see, I have evidence that I was launched in a rocket. Should probably use red for that. There we go. Was launched in a rocket. I did get into space. I ate most of my cookie because I was a good boy. And today we're going to talk about analog modulation. All right, so I want to back up a little bit before we begin. The first thing I want to address is the idea of capacity. So we already started talking about analog and modulation a little bit, but there's some things that are going to come up later that are going to be relevant, and I wanted to revisit a question that one of you guys had in class. So right here we have the definition of capacity. So in the real additive white Gaussian noise case, when we're considering capacity, there are a couple different ways that we can represent it. We can do bits per second or bits per use. Basically, one is based on the bandwidth that we're using, and the other one's just based on single uses of the channel. So the real difference that I wanted to point out here, though, is the fact that between real and complex, there's a very significant difference, which namely is this extra factor right in here. Now, the reason for this is pretty simple. For real signals, we have symmetry across the origin, and so everything's kind of duplicated, if you will, and there's no additional information on both sides of the frequency axis. So we're going to talk about that towards the end of this lecture. But I thought it was kind of interesting to point out. And then also when we're talking about bandwidth definition of capacity, it doesn't actually change when we're thinking about the bandwidth, which is why we have a slightly different definition for bandwidth when we start to think about complex signals. So again, stuff that we'll talk about down the road, but nice little addendum to put on the radar here. All right, so the big takeaway here from all of this is real signals are symmetric in frequency with respect to the axis for magnitude. Now here's a little diagram that we looked at before. We discussed kind of how we're going to break out all these different amplitude modulation schemes. The first one was this double sideband suppressed carrier. The one we're going to talk about today is amplitude modulation. This introduces a carrier in the frequency domain that's not suppressed, right? So this one doesn't have that carrier going around when we receive it. This one does have the carrier in it, and that's why it's a true amplitude modulation, if you will. And then single sideband basically asks the question, if we're replicating all this information at both the positive and the negative frequencies, can't we get rid of some of that? I mean, isn't this a little redundant? And so single sideband is going to answer that for us. The answer is yes, but there's a little bit of a trade-off. So we'll talk about that today as well. All right, so digging in, you may recall from lab that we built an envelope detector. The purpose of this was to beat things back down to baseband. That was with this low-pass filter. But we also used the rectifier to actually build the proper envelope for the signal that we were looking at. So we just needed the top half of the envelope. If you remember, when we build envelopes, they look something like I might have some kind of wave right here. If this guy's sitting on the top, as we had in lab, then I'm going to have a symmetric version. Oh boy, I shouldn't have done this on the fly. I drew everything ahead of time, and then I always got to draw something myself, apparently. All right. There we are. And then we're going to modulate inside of here. And we'll see another example of this later. But the carrier for this signal is at a much higher frequency. That's because we got to get through a number of cycles in order to even see this darn thing. But mostly it's because we're kind of just, much like I did here, kind of scribbling in the space and pushing this up to a much higher frequency so that we can actually transmit it. And it's much easier to transmit this thing, weirdly enough, than it is to transmit, I should say, this thing. So our message actually lives in either the positive or negative portion of this envelope. So this is all this stuff here This is all juicy information, okay? And for AM signals, we only need the top part. We talked a little bit about if the message was crossing the origin. That was going to introduce some issues if we just took an envelope detector like this. But for amplitude modulation, that's not going to be the case. But our message is in the envelope, so we can just extract it from there once we pull it out from the receiver. So this is the general form that we have for double sideband amplitude modulation. You can see here pretty clearly we are taking our original signal and we're normalizing it. So now it's going between plus and minus 1. And then we're rescaling it with this factor mu, adding 1 to it to push it up. And then some kind of gain factor, who cares? And over here, we're just going to multiply by that carrier. Again, this is a much higher frequency than anything that's contained in MT. Okay, so let's look at some actual pictures of this process at work. So here, off to the left, is my original signal, my original MT. And it's just living its happy dumb life over here. It's got a zero mean, which is really important for some of the things that we're going to do later on. Namely, it makes it a lot more simple. So that is, if we're flipping these, some kind of encoding scheme, we're generally assuming that adding the ones and the zero together, their versions that we have encoded, are going to cancel each other out when we look at the DC average. Okay, when we just look at like what is our average output here. Okay, so when I divide by MP, MP being the upper and lower bounds of MT, what I do is I normalize. And mu is basically the scaling factor. You can think of it as kind of relaxing a little bit the bounds. And one of the reasons we might want to do that is so that we always have a little bit of space. You can notice right in here, when I built my my carrier, if I had this so that there was no space inside of here, I would, at some point in time, maybe completely lose my carrier wave. It would go out to 0 in terms of its amplitude, mostly because this thing would be touching the bottom. Some cases that might not be very desirable, and especially for telemetry streams or for trying to make sure that if I lose contact with something, maybe I want to terminate something. So we had missile systems where they'd fly around, and if we lost some kind of tracking or signal on them, we really don't want them going awry. So maybe they have some kind of auto termination system if they dig to not picking up that carrier wave anymore at any amplitude. But we still need to transmit signals and stuff to it. So we might want to use some very small mu factor here. We know that we're going to get a good signal through when we do, and maybe we could use some error correction codes, something like that. But on the whole, if I'm not seeing that carrier wave at all, I don't want any more business with flying that missile around. It's not going to mind of its own, so let's put it in the dirt. So there's reasons why you might want to do this. Even though you get better resolution by keeping mu at 1, you might not want to do that. All right, so again, another reminder here. Assume that MT is 0 mean. This is going to come up. All right, so if I break this apart, I can actually see exactly what's going on here. I have this form right here. A is just going along for the ride, who cares? I'm going to break this up into 1 and the part that actually has the message. And you can see this extra 1 here, actually, it's not doing anything. It's just sitting there, and when I distribute A and this cosine 2 pi FCT, which is the carrier, I end up with just the carrier, and here's a little carrier pigeon, right? It's carrying the message, but it's just getting added to the scaled SB or DSB, double sideband, suppressed carrier signal. So I've got a suppressed carrier signal with the carrier, so it's just a double sideband or a double sideband amplitude modulation. So we can just put a little wiggle on our carrier, add that to the pigeon there. He's going to carry it for us, and we're off to the races. Okay. Now, what does this look like in the frequency domain? Well, a pure carrier wave is just going to be some amplitude A, and it's getting split over the positive and negative frequencies for the amplitude. And recall that when I think about impulses, they do have a quote-unquote amplitude or a height. It's just multiplied times infinity. Never mind that for the time being. But if I have a pure impulse, essentially, I'm taking an impulse at that frequency. I'm sorry, if I have a pure cosine wave, I'm taking a pure impulse at that frequency, so that's the red line there. And then my actual information is all stored in the green areas here that you can see in the double sideband. So I have 4 replicates of this information. Yikes. And that's all going across the channel, by the way. When I break this up and think about it in terms of the actual transfer function, if you want to call it that, then this is what I end up with. Capital M here being the Fourier transform of our original message. Just have some scalars attached to it, and then these delta functions are just going to go along for the ride. So again, the big takeaway here is that my impulses are just wasting power. Okay, they're not actually contributing anything to the overall signal process at this point. We're going to see what benefit they actually provide, though, because like we said back here, my envelope I can just peel right off the top, and that's a very valuable property if you don't want to have to figure out whether or not you're supposed to take the top part of the envelope or the bottom part of the envelope. In particular, if it never crosses the axis through 0, then you always know where the correct envelope is, yeah? So that's why another reason why mu might be handy. Okay, so in summary, basically what we get is double sideband suppressed carrier is very power efficient, but we need to synchronize the phase as we learned last class. And double sideband amplitude modulation wastes power, but actually we don't need to sync anything up because we have all the information we need right out of the gate. We do have to think about, generally for these signal processes, which direction the information is flowing. If I have a big AM radio tower, I'm never transmitting to that AM radio tower. I mean, they still won't play my song even though, they play all kinds of garbage on the radio these days. Oh well, maybe someday the accordion will be more popular, but for right now, I'm not going to win. Take this off here. Sorry, the fan in my hotel room kicked on. All right, so the average transmission power of AM for double sideband is kind of a very dense calculation, but there's a few critical areas in here that are very helpful for being able to compute the average power of any kind of transmitted signal. Some really good proof aspects along the way that you can use in other average power calculations. So that's why I'm going to go through the whole derivation here, and it's something that might come up on an exam or on homeworks that you might see in the future. So I want to make sure I cover this for you guys. So here we go. When we talk about average power, this is the definition, okay? We square the signal that we send, take its integral from minus t over 2 to t over 2, and we look at the expectation of that. The expectation, of course, is only applying to the signal itself because that's the only part of the random process. The message is the only random aspect of what we're actually sending, unless we have some noise or something like that we're going to account for here, but we're going to ignore those effects in our message component for right now because this is just the stuff that we're deliberately transmitting. Now, When I take this limit, I take 1 over t because I'm trying to take an average of the power. And this average is going to go all the way out to as far as I can go. I'm basically looking over a very, very, very wide window of time. And when I do that, I need to normalize it with respect to, well, how long I looked over that time. And so that's what this 1 over t is doing here. So we've done some average power calculations in the past, but I want to refresh us on why this equation looks the way it does. The other thing, too, here is we can think of g squared t as sort of an inner product of g with itself. Anyway, moving on. We have, using the definition now of the double sideband amplitude modulation, what we have is all this junk squared. So every part of GT gets squared, every factor. And so the A gets squared, this 1 plus this stuff gets squared, and also the cosine that's attached to it, the modulation scheme that we use gets squared. So as a sidebar exercise, I wanted to walk through the cosine squared integral because it's going to become relevant when we start to compute the overall average power. So when I look at the cosine squared, I can use a trig identity to rewrite it in this form. Let me get rid of some of the junk. And when I rewrite it in this form, I can break it out into 2 terms. I get the 1/2 term here and then the cosine over 2 term as well. So the 1/2 term is pretty straightforward. I'm just integrating 1 over 2t over the bounds of minus t to t. And then the other portion here is a cosine function that I'm integrating symmetrically with respect to the origin. This is very important because this goes to approximately 0 as I look over a very, very, very wide interval. So you may think, oh, well, cosine's, isn't that symmetric with respect to 0? And so if I integrate that, wouldn't it just be positively oriented? Well, I don't know. Well, what you really have to think about here is essentially what we're looking at when we take t to be very, very large is we're looking at the DC component of the cosine, which doesn't make a lot of sense. That's why it's approximately 0. So as we get larger and larger in our time window, this whole thing goes away. And so we're kind of just left with the 1/2 at the end of the day. And this is why when we did our derivation before for just a cosine 2 pi FCT, we ended up with a power of a squared over 2. You guys may remember that from, what was it, like a month ago now. All right. So returning back to our original problem, the first thing I want to point out is this guy here, and in particular this factor, okay? So in that factor, we can go ahead and take, I've got 1, 2 terms here, and they're squared. So what I do is I break out this entire quadratic, and then I'm going to break up the integral into these 3 term components. Now, you may recognize here that in the first one, I'm just going to have a constant, which is going to make this really easy, times a cosine squared function. So that's going to really be useful for, we're going to get a lot of utility out of the stuff we just did. This other part here, we're going to find goes to 0. And then the last part is basically going to be what we would have with a single, with a double sideband. So let's go ahead and break this down. I splay this out. I've got my 3 terms, 1, 2, 3 here. I don't know if you can see that. That's 2, 1, and 3. And then here's my first term, and my second, and then my third is down here. Okay, so these are the 3 terms we're going to look at. The first term, we can almost guess what this is going to be, right? We've already computed it. It's just going to be a squared over 2. The second term is really interesting because in this one, mt is no longer squared, and we have to apply an expectation of this. I think maybe you can see orange better, but we have to apply an expectation of this. So this expectation is going to push its way in and just hit the random processes that it has along the way. Everything else is constant with respect to this and well known. Even the cosine function is not a random process. Only MT is a random process. And so when we look at the expectation of the second term, what we end up with is an expectation of MT directly. And we specified earlier that our signal was zero mean. So the expectation of that signal, the DC component of it, should be zero because all of our positives should roughly balance out with the amount of negatives that we have in terms of voltage or whatever we're using for transmission. Okay, so that gets rid of this whole term right here because all of this just goes to zero. That's lovely. Now, for the third one, this is actually pretty simple still. We have this expectation that's going along for the ride. Presumably, this is a well-known, well-understood quantity, and so it's not really going to change with respect to time necessarily. So that makes our lives a lot easier. We do have to assume, however, that this is an ergodic process, which essentially means, in the nicest way possible, that it spreads out nicely over the region of randomness that we're dealing with. So after the random process gets going, it tends to just spread out over the region of possibilities. Okay, so that's in a nutshell what ergodic means. There's no funny business or no funny patterns with the initialization of a certain value is going to make you spiral off. Some of you may have seen things like strange attractors and stuff like that. These are not going to be nice ergodic processes, right? Because it really depends on where you start, what kind of seed you have in those cases, where you're going to end up. But for us, honestly, flipping a coin, heads or tails, eventually I kind of expect to have as many heads or tails equal to each other, assuming my probability is 1/2. So stuff like that, right? We're going to kind of fill up the probability space according to the expectations that we see. So that's a long-winded way of saying, don't worry about it. Sorry. If you're still with us and you're not asleep, on we go. Here we go. So we have the double sideband component is just this section right here. And this carrier is actually just sitting by itself. So if we were to compute just the double sideband suppressed carrier by itself, we would have some kind of component like this. Remember that we use D as a kind of gain factor on the double sideband suppressed carrier before. So we've overshot on power by a squared over 2, not as a factor, but as an additive amount of power, assuming we set D squared equal to A squared mu squared over MP squared, or D is equal to A mu MP. So in short, this is how much extra power we're burning up by doing this. But it does bias a little bit where we don't have to worry about synchronization. So the next question we have is, can I do this without having 4 damn copies of this signal flying about in the frequency domain? And the answer is yes. So I only need one Jeep in my life, right? I've got my crusty old 93 Jeep Wrangler. I don't need 2 Jeeps. I can get rid of this guy over here after I've pushed this thing up and modulated it using the carrier, right? Now, I want you to note over here, this is very important, okay? Look over on the left. Now, I can't do this before modulation. Why? Well, we're going to do something like this later on, just as a spoiler alert. But for real signals, for just real signals, all the stuff we've been doing with so far, we can't get rid of this other half because every real signal and every real system that we look at has to have symmetry across this axis. So if I just knock this out before I even get started, I'm going to have a bad time, okay? Now, we're going to do exactly that later on today. So just hold on for a minute. But for right now, we can't do it. So we have to push our signal up, our baseband up into the carrier frequency, and then we can use a bandpass filter to get rid of the unwanted component, the unwanted duplicate on one side or the other of FC. So here's how this works. block diagram wise, we take our incoming message right here, we modulate it with a cosine. Remember that when multiplying in the time domain, we're essentially convolving in the frequency domain, so we're just pushing it to FC. We use a bandpass filter to pick either the high portion or the low portion around FC, and then that's what we transmit. We just transmit essentially half or one duplicate of the original signal as opposed to both. This goes over the channel, and then we beat it back down to baseband using the same cosine function. So remember that when we beat back down to baseband, we're essentially multiplying in the time domain, which is kicking us back to a convolution in the frequency domain that's mapping us to from FC over to 0 and to 2FC. So we lose the stuff that we had here when we demodulate, and it gets kicked 2 copies. One goes to here, so I get this guy projected here, and 1 copy goes back to the origin. Okay? And then, of course, I get it from the other side, too, at negative FC. So that also happens. Suffice to say, we throw this part away, and we just look at the baseband. And in order to just look at the baseband and throw away the right side, maybe I should use red, right? And we just want to look at the baseband part. We have to use this low-pass filter right here so that we can just isolate that portion. And actually, I made a little boo-boo here. Ooh. So because we did this bandpass filter, essentially when it got transmitted, it was just this part here. And so when I make copies, they just go here and here like so. Okay, let's see this in action a little bit. Here is the modulation scheme. So you can see the filter acting right here. As I move from ZT, which is the output of the modulation, to the output of the bandpass filter, you can see that I get rid of one of the sides of the modulation scheme that we have. We also get some kind of gain factors in here. There's kind of an arbitrary gain factor assigned, K/2 for the initial modulation. Then we'll have some kind of gain for the filter. So USB or LSB, this is just, we can pick from either the upper sideband or the lower sideband as we go through. All right, now if we zoom in on this process, this is actually a really important diagram for using the equations. So we kind of end up with like a shopping list, right, for where we want our bandpass filter to operate. So we have the lower stop band, the lower pass band, the upper pass band, and then the upper, stop. Oh, good grief. All right, there we go. And the upper stop. Okay, and these points are going to designate for us how we're going to build our filter. This is probably my favorite one, but I won't say why. So let's move on here. We've got FSL is defined as having to be greater than or equal to FC minus BL. You'll notice that BL is sort of the region that we have between where we were at the origin and when we started having some kind of information. So for like audio stuff, this is going to be in the hundreds of hertz range. Well, it could be even lower actually, but it's going to be off of 0. So we're going to have a little bit of band between the actual carrier frequency at FC and where our actual information starts to pick up. The more berth you have there, the better off you're going to be when trying to build this filter. It's going to be easier to build if you have a more narrow band that you're trying to filter over here, so you can make this taper off a little bit easier for the slope. Okay, so you did some of this kind of stuff in 300, but these are the criteria that we have for trying to pick these points. And then typically for our filters that we're going to build with simple components, we're going to end up with this equation. The quality of the bandpass filter is just going to be your center frequency divided by B, and B is going to be just this region between here and here where the information sits, not from FC all the way out to FPU. And then our transition ratio, which we talked about a class or two ago, is just going to be the difference of the stop up or stop lower divided by the pass up or pass lower. All right, so here's a real quick example. We've got a center carrier frequency of 100 kilohertz. We have a lower band. This is kind of the 200 hertz before we start picking up any kind of audio, right? And then maybe we go up to 3200 hertz for that audio. So this is kind of in the speech range, I think. Well, maybe, I don't know, this might be a little high for speech, I'm not sure. But this is kind of a typical AM scheme. And so if we look, we can try to find Q and T and things like that. But what we end up finding is that when we compute all these guys out, we end up with a transition ratio, right, of something that's a little less than 2. And so we get kind of a challenging design. And so sometimes with single sideband, the challenge isn't so much getting this thing decoded or demodulated. It really is getting the signal sent exactly in just this portion that you're trying to get to up at that higher frequency. So for this one in particular, if we use a 16th order Chebyshev, which you guys kind of learned about in 300, I believe, you can see here that the cascade of system here, just keep on popping these guys in here as much as we need until we get that filter as tight as we need it to be. And then we have our resistive load on the end here. All right. So sometimes the filter design can make SSB challenging, which is why we need, but we also need, a low pass filter architecture at the receiver. This actually isn't really that bad usually. It's a one-time cost, and we don't need to move it all over the place if we change signals. It can be pretty general, because assuming that our carrier is high enough, we really just need to pass anything that lives in here. So generally, as long as we're reasonably below the carrier frequency that we might want to use, we're good. So these are going to be a lot easier to deal with. And you can see here how this works. We just take this portion over to the right here. It could be the portion over to the left too. Again, by the way, we could throw this part out and just keep this side. I'll be specific if I want you guys to use one versus the other, but I think for most of the examples that I would pull from for like an exam, I just pick the one that we kind of use in class as a poster child. So when I convolve this in the frequency domain, because I'm multiplying in the time domain, then what I end up doing is making multiple copies. Right? I make 2 copies from this guy bouncing into, these 2 guys bouncing into this guy over here. And I get one that's mapped to the origin, and then the other one gets pushed down another FC to the right. So this one's the one that's actually working for me. It's pushing it back to 0. Interestingly enough, we pushed it out originally with this portion, and then we pushed it back with this portion. So I think that's kind of cool that both sides of the real sinusoid are working in our favor for pushing us into a space and then pushing us back out of the space. It's kind of wild when you think about it. In any case, our overall gain is going to be something like K times the gain, the whatever gains we have off of those 2 filters, the low pass filter and the band pass filter, divided by 4. This is just how many times we've kind of divvied it up and added it back together again, times the original signal. All right, so next we're going to talk about the Hilbert transformer. Yep, and this is David Hilbert, and he is currently dead and rolling over in his grave from this monstrosity that I've constructed here. So why do we care about the Hilbert transformer? Well, the Hilbert transformer is a very, very elegant mathematical way to do the very thing that that we talked about, which is phase shifting. Or it ends up being phase shifting, but we want to try to build more complex signals, right? We'd like to be able to do these kinds of operations without just thinking about funny business with bandpass filters and all this kind of stuff. So the Hilbert transformer essentially provides us a new mechanism for manipulating our frequency domain. So the big question I had when I first saw this, because this is kind of how we should be trained to think, right? Is this an LTI system? And we care about that because it has implications for real implementation and modeling and all kinds of other stuff. So yeah, this is actually an LTI system when we think about it, but it's not necessarily causal, and it suffers from a more realistic limitation, which is that we may need to discretize it. We also have in the frequency domain these complex things, whatever that means. So we're going to have to explore the mathematics of this thing, whatever this thing is, in order to really get a handle on why this might be useful. So if you can imagine when this first came out, you might not know what to do with it, but it actually does serve a really cool purpose. So when we bring in a signal, we're going to build a new kind of modulation scheme here. This is going to be the single sideband, and we're just going to take the upper sideband portion. So this is the USB upper sideband, single sideband. But the nice thing about the Hilbert transformer is it retains Hermitian symmetry. Suffice it to say, you don't need to know what Hermitian symmetry is for this class necessarily, but if X goes in real, Y comes out to be real too, which is kind of a surprise considering that the Hilbert transform is essentially multiplying by an imaginary number in the frequency domain. It maybe, when you think about that, it's, an imaginary number in the frequency domain, that's just a constant. And wouldn't that constant kind of push back out? Well, it does in a way. So the top line here is what we're going to follow first. This is actually old hat. We push this signal through, and we modulate it with a cosine wave. Well, that's easy. I just take this thing that was at baseband, and I push it to the carrier frequency, whatever this FC is, and minus FC. So I have two copies of the thing. Blah, blah. We've heard this all before. But what happens when I take the same signal now, and I push it through a Hilbert transformer? Well, the positive portion, before I modulate it, the positive portion is going to get mapped down to minus j times a. We're not using magnitudes here. We're using the no kidding frequency plot. And the negative portion is going to stay positive. So now I get a flipped version of this triangle picture here. Now, obviously, we're not transmitting triangles in the frequency domain, right? This is just an example of a shape to kind of show you the features in the best way possible so that you can see what's going on. The red regions of the top and bottom here are going to cancel each other out after modulation and addition. So I'm going to modulate the bottom part by minus sign at the same carrier frequency. And what minus sign looks like is an up and a down. And you may see kind of a similarity here to the Hilbert transform, which essentially fixes this to be symmetric with respect to the origin. Even though it's got these weird components now, we're really close to getting the result that we want, which is that single sideband result. If I add this to the original one, the reds, again, they cancel out. The greens are additive, and I end up with just the right part of the wave. And that's just all the information that I really need if I have to transmit a real signal, because I can't avoid transmitting this and this at the same time for some kind of real signal. So what is the Hilbert transformer exactly? I understand what it's doing now. It's basically building that, it enables me to do things like building the single sideband. There's many other uses for the Hilbert transformer, but in our particular application, that's the first thing we're going to use it for. But what is it actually doing? How's the sausage made, as it were? Well, if we look at an input, which is just a cosine wave, then we can use Euler's rule, or Euler's identity, to build this thing as, e to the j2 pi fct, e to the minus j2 pi fct. And we can pop this through the transformer and see what we get out. Well, if I push this guy through, and then I tack on some j's, and positive and the negative, I end up with something that looks pretty darn familiar. This is actually just a sine wave. And actually, I think this is supposed to be minus. I think the notes are wrong about this. So this should be minus here. So I end up with a 90-degree phase shift on this guy. Because that's what cosine and sine are. But I end up, most crucially, with a real signal. This is real. So I've done all this imaginary stuff to my signal, which was just a pure cosine wave. And I've made a sine wave. I've made a phase shift with this thing. So it's a pretty neat tool. All right. So I did promise that we were going to start manipulating things in more complex ways and be a little bit more flippant in the frequency domain. So far we found that all the information we need is contained in a narrow band of frequencies near FC. Usually is on one side. Let's write it this way. Usually on one side of FC and duplicated on the other. Okay, so when we go back down a baseband, we kind of can think of it as just the positive portion, but we can't actually just extract that until now. So given any general real valued bandpass waveforms, can we find a more general representation so that it can essentially extract the features of the signal that we're trying to send? Now, this is a very convoluted way of saying, is there a way that we can just look at, let's do orange. We get rid of this crap in the negative FC, right? And we'll get rid of some of this other crap right here. And maybe we can just do something with just this. Because I don't need all these duplicate pieces of information. That doesn't do me any good. So is there a way that I can transmit just this thing in the frequency domain? And are there any drawbacks? That's always something we have to ask ourselves. Is there a way to do it? And then what did I cost myself in order to do that? And you might think, well, why would I want to get rid of the duplication anyway? What's so wrong with that? There's nothing wrong with it. That's why AM radio still is popular for irate, talk show hosts and sports. I don't know what else is on AM radio. I don't think I've listened to AM radio since I was 7. But it's important, I'm sure. Anyway, here's an overview of the complex envelope. So here's how it works. What we're going to do is we're going to want to take just a single side of whatever we're working on here. We're going to discard the negative frequencies before we even get started. So when we shift it, though, what we want is to choose some kind of reference frequency that lives inside of here at F naught. Doesn't have to be at FC necessarily. But something kind of close would be good. And we're going to backshift this and pull this whole thing over to live right at the origin. Okay? So that's essentially what it's going to do. It's beating it back down to baseband. And in case you don't know who this fabulous person is, this is the funky bass player, Victor Wooten. The result is also very funky. We get something that's not quite symmetric across the frequency axis. Okay, so when we map out the complex envelope in the frequency domain, this G tilde of F, it's a little funky. Okay, so I don't know if any of you guys read Pete the Cat, but there you go. I'm getting a little loopy here since we got all this. It's getting kind of late. Recording this the night before. Let's see here. So the upshot here is that in the time domain, this is our representation of the complex envelope in the time domain. Along with the value of F naught, this retains all the information we could possibly need about the signal. This is fascinating because when we think about it, we're using some tools and techniques here that in real space, real time, not sure how they're really working. But let's just follow the math and see where it takes us. As long as we cling on to how much we pushed it, we can actually reconstruct the signal, no problem. All right, G hat of t is a complex valued time function. Okay, whatever that means. And G hat of t is the baseband signal. It's a baseband signal because it lives right here near the origin. All right, so here's a theorem. We're not going to really prove it very overtly, but the theorem is this. All real baseband waveforms can be represented by taking the real component of some complex envelope of G. And you say, well, okay, I guess that makes some sense. But what that's essentially saying is that there's a way to go in either direction. We can either take a real bandpass waveform and extract its complex envelope, or we can consider the complex envelope modulated by this thing, take the real portion, and we get back the real bandpass. So it kind of goes both ways. All right, so we're going to look at some carrier waves. They go brrr. And here we go. I start off with a very simple signal. Just some kind of cosine that's been phase shifted just a little bit. All right. Then if I write this using Euler identity, I can think of this as two parts where Z is an imaginary part plus a real part plus J times an imaginary part. The result here for the real bandpass waveform is just 2 times the real component of Z, which in this case is equal to that. And Bob's your uncle, which is great because we're going to run into Bob later. Or we ran into Bob already. Where'd Bob go? Oh, hi, Bob. There he is. Anyway, sorry, I'm really losing my mind at this point. Okay, we we end up with this for the complex envelope. So, in summary, I started with this real cosine that was phase shifted. The complex envelope version of this is just this complex sinusoid that's been phase shifted by theta. Pretty straightforward. I mean, this is essentially the way we like to think about sinusoids. So this is looking pretty darn good. And good work, Dr. Hilbert. By the way, I'm mathematically related to this guy, I think. He's in my genealogy tree. So my advisor's advisor, somewhere along the way. Anyway, off we go. Complex envelope just looks like this. All right, so that's great. How do I practically use this? Well, If I look at amplitude modulation now, what does this look like for complex envelope? Because I know a pure cosine, yeah, okay, pure cosine waves, I know this. They're just these little things that orbit around in the complex plane. Their amplitude is how far away they are from the origin. The amount that they rotate is their phase. Cool. How the heck do I deal with this thing in the complex plane in that same fashion? Well, it's actually pretty straightforward. We just go back and we use the same kind of identities that we used in the previous exercise. And we say, well, this cosine here, I can think of it using Euler's identities, and I'm just taking the real component to get back GT. And so when I extract this function that's living next to this guy here, I end up finding the complex envelope. So this is my G tilde T. So the trick here for these problems is go back to the definition. We have to think about what our original real waveform looks like. We then say this had to be the real portion of some complex function times this was essentially a sinusoid at a specific frequency. That frequency, by the way, is just how much we're shifting to put it back at the origin. So that's all that's going on here. You'll have to rearrange things sometimes for some signals because some of them look a little funny, especially if you start getting to kind of some of these sync functions and things like that. And you're just going to use the part that isn't the wiggly noodle, the part that's not the sinusoid, okay? You're going to look at the real portion, the real coefficient of a sinusoid that gives you back, when you take the real component, GT. Okay, so that's where we're at. Oops, don't want to get rid of that. All right, so bypassing a proof here, I'm going to conclude with this. We can show that if I write the Fourier series of this, and I should probably add here, this is a really big deal. Okay, we're extracting all of our information that we need by sort of throwing away the sinusoidal aspect of our signal, the modulation aspect of our signal, and we get all the essential information by looking at just not the real component necessarily, but just what's being multiplied here on the inside. So I think that merits a whoa, probably. I don't know. This is probably before your time, but I think he's just now known as Whoa Dude Keanu Reeves. But this is from Bill and Ted's Excellent Adventure, which is awesome. So that's your movie recommendation for this weekend. It's actually so-so. I would give it a 4 out of 10. So raving reviews over here. Anyway, back to what I was saying. The Fourier series, if I look at this guy here, its complex envelope this is in baseband, but its complex envelope here just takes on this form. So you can see that all the coefficients remain intact, and I effectively am just rearranging some terms here and shifting them over. So nothing too crazy over here. So next time we're going to talk about quadrature and polar representations. I love when we get to quadrature stuff because it just makes life really so much easier, and quite frankly, it's just a more general way of dealing with all these weird complex numbers and signals and things like that. IQ is just awesome. So I look forward to teaching you guys that and reviewing it in the meantime. So anyways, I hope you all have a very happy Friday, and I'll see you all on Monday, hopefully. Looks like we might get some rain out at the range, so I don't know that we're going to launch on Saturday. I might not get back until midnight on Sunday, and considering that I'm driving, boy howdy, we might be for a rough time on Monday. So, again, I reiterate, a whoa dude here, but probably for a different reason. Okay, all right, see you guys all later. Ta-ta.